Hi there. In this video we're going to talk about the concept of partial derivatives. We'll begin by talking about the derivative that we learned in Calc 1, and then we'll extend that idea for multivariable functions, and that'll give us the notions of partial derivatives. So let's do that. Let's review what the derivative that we learned about in Calc 1 was all about. So what we're looking at here is the graph of a function. And let's talk about its derivative. So to do that, I'm first going to have to choose a value for x. Let's call it a. All right, so here's my value for x. I can change its value however I want. Now what I want to do is I want to go up to the graph and get a point. All right, so there we go. And I want to now draw the tangent line to the graph through that point. So I'll do that. There it is in green. Okay, and you can see as I change the value of our x-coordinate, the slope of that tangent line changes. The slope of the tangent line is the derivative at a. That's the derivative with respect to x. And that's what the derivative is. It's the slope of the tangent line to this curve. Okay, well now let's go to the multivariable function case. Okay, so when it comes to multivariable functions, and let's start by thinking about just a two-variable function of just x and y. All right, we can take two derivatives now. We could take a derivative with respect to x, or we could take a derivative with respect to y. Well, what does it mean to do that? Well, if I'm taking the derivative with respect to x, I'm only changing the x. I'm only moving in this direction, right? And so that means I'm treating y as a constant. So let's take a look at a graph and see what that means. Okay, so here's a graph of some function. Now I'm going to treat y as a constant, so let me fix y equal to a constant. When I look at what that means as far as the graph goes, I can see it's tracing out a curve here. So what curve is that? Well, it's this one. Right? Now let me get rid of this other stuff because it's that curve that's now of interest. That curve is something I can differentiate using single variable calculus techniques. So if I look at the rate of change of this curve with respect to x, I get a tangent line. And you can see that tangent line right there. Right? The slope of this line is the derivative with respect to x. Now, like I said, there are two derivatives we can take. X is only one of them. So we actually call that the partial derivative with respect to x. That represents the slope of this line. Let me put the graph back so you can see how that fits on top of everything. So if you see what we're doing here, we're only looking at the way the graph is changing, the way the function is changing in the x direction. It has nothing to do with what y it's doing in the y direction. Right? It's just looking at the x direction. So we're finding the slope in the x direction only. Now we can do the same thing with respect to y. We can look at the partial derivative with respect to y. Let's do that. Well, if we're doing that, that means we're treating x as a constant. So let's do that. Right? That will intersect the graph on a curve. Where are you, curve? There. I have to rotate. Okay, the curve's not really showing up. I think when I delete the, let's go ahead and delete this plane here. Maybe it'll be, yeah, there we go. Okay, that's the curve, right? And when we take the derivative with respect to y, we're getting the slope of the tangent line to that curve. Right? And as you can see, the curve isn't changing at all in the x direction. It's only in the y, right? So on the surface, again, you can see what we're doing. We're just finding the rate of change in that y direction. Okay, now you can do both. You can consider both of these, right? So we got, let's set there, let me just make sure we're at the same point on each curve, right? There we go. And you can see in the full picture, at a point for the function, we have an x derivative, the slope of this line. That's the partial derivative with respect to x. at that point. In this case, it's at the point 1, 1. And we have the partial derivative with respect to y at the point 1, 1. And so we're getting the slope of this line and the slope of this line. And that's what the partial derivatives give us with respect to a multivariable function. Okay, so we just talked very conceptually about what those partial derivatives represent. What I want to do now is do it analytically. Just write down on a piece of paper, let's compute these partial derivatives. So let me write down what the function was we were just looking at. This was our function. Now, what did we do? We computed the partial derivative with respect to x at the point 1, 1. And we computed the partial derivative with respect to y of the function at the point 1, 1. This is one way to write it. Another way to write it would be to write it like this. By writing a subscript, that means that we're taking the partial derivative with respect to that variable. Now, you can see this looks a lot tidier than writing it like this. Why would we ever use this notation? Well, the reason is that this is a convenient symbol that we can just slap in front of any function, right? So any expression, in fact. You can't put a subscript after an expression, right? People won't know what you're doing, right? But you can always slap this symbol in front of an expression. So that's the utility of this symbol, and that's why you definitely want to come to terms with this. This is called Leibniz notation. And so you should know both of these notations. They mean the same thing. And so when we're doing the partial with respect to y, I would just write like this. They mean the same thing. Now, what does it mean to do the partial derivative with respect to x? Well, I'm just going to treat y as if it were a constant, and I'll differentiate this whole thing with respect to x, just using single variable calculus techniques, but treating y as a constant. So the 3 comes down, and I subtract 1 from the exponent. So I get negative 3/4 x squared e to the y. But I'm evaluating it at the point 1, 1. So the evaluation symbol is a vertical bar, and then down at the bottom, I'll just put 1, 1. Which means that in the next step, I'm going to plug in 1 for x and 1 for y. And so I just get negative 3/4 e. Okay, let's do the same thing for the partial derivative with respect to y at the point 1, 1. Well, now I'm differentiating with respect to y, so I treat x as a constant. The derivative of e to the y is e to the y, so nothing really changes here. I'm evaluating this at the point 1, 1. So what do I get? Negative 1/4 e. So 2 different derivatives. And those derivatives are the slopes of those lines that we were looking at in the 3-dimensional picture.